Good morning, students. Welcome to lecture 4 of module 4. So, today we'll start oscillators. Now, the definition of oscillators are the circuits which generates periodic signals of constant frequency and amplitude without the application of any external input signal. So these are the particular circuits which will provide oscillations like this. So one oscillation will be one cycle. Clear? One oscillation is one full cycle. Now here it will produce constant frequency with constant amplitude. Can you see this particular signal? It is of the same frequency and same amplitude. Clear? And this will occur without any external input signal that is going to be given. So once you give the DC power supplies, the circuit will function and it will provide oscillations like this. So the different kinds of oscillations we can produce is a sinusoidal wave. So in sinusoidal you will have both, that is sine and cosine, and the other types are square, rectangular and triangular waveforms which will look like this. So these are the different kinds of oscillations what you are seeing, and we can tell the particular oscillation is of low frequency, where you can see if we take this particular time interval t, I have only one cycle of oscillation, whereas within the same time interval of t I have three cycles of signal. So this is of higher frequency, this particular oscillation is of higher frequency when compared to this. So these are low frequency and these are higher frequency oscillations. Now when we speak with respect to the classification of oscillators, oscillators are classified on the basis of the operating principle. So the first one is feedback oscillators, and the other type are the non-feedback oscillators, which are nothing but the UJT relaxation oscillators, that is unipolar junction transistor relaxation oscillators, based on the type of the waveform. So if the type of the waveform that it is produced out of the oscillator, if it is sinusoidal, which produces sine waveform, so this is also called as harmonic oscillators. For non-sinusoidal or also called as relaxation oscillators, which produce the non-sinusoidal signals like square wave, sawtooth wave, triangular wave kind of oscillations, shape of oscillations. And depending on the components used in the oscillators, you have RC oscillators, that is resistance and capacitance oscillators, LC, that is inductance and capacitance oscillators, and crystal oscillators, negative resistance oscillators, that is your tunnel diode is used in this particular kind of oscillators. So here we are using cluster to is the component that is used in this oscillator. R and C components are used in this particular oscillator, and LLC is the components used in the particular oscillators. For your syllabus, you have the RC oscillators. Clear? And the next type of classification is based on the frequency, on the frequencies that is produced by the oscillators. So the first one, depending on the audio frequency oscillators, this oscillators produce the audio frequency range signals. So the oscillations will be of a frequency range of the audio frequency. Next we have radio frequency oscillators, very high frequency oscillators, ultra high frequency oscillators, and microwave frequency oscillators. So this is with respect to the classifications. Now coming to the major part of these particular oscillators is the entire chapter of oscillator revolves around this 2 points which we see. So if we see this particular 2 points, we have the first point, the closed loop gain, which is given by A into beta, A standing the gain of the amplifier and beta is your feedback factor. So the product of this, so the closed loop gain, that is A into beta, the product of this must be equal to 1. Clear? The first Parkinson criteria for oscillations is, the first point is the closed loop gain, that is A into beta, must be equal to 1. The product of this should be equal to 1. The second point, the total phase shift around the loop must be equal to either 0 degree or 360 degree. That is, the entire phase shift of that particular circuit should be either equal to be 0 degree or 360 degree to satisfy the Parkinson criteria. So these 2 points, please remember when we are doing the derivations or the furthermore topics, we will be repeating this two particular things. So the first one is A beta, product A beta should be equal to 1. The total phase shift of that particular circuit should be either 0 degree or 360 degree. So the above two conditions must satisfy to get a sustained oscillation. We'll see later what is the meaning of sustained oscillations. Now, the other points to remember is all oscillators will consist of an amplifier consisting an active device and a frequency selective feedback network. It will also have a feedback network to determine the frequency of oscillation. Clear? So we will, any particular oscillator will have an amplifier and also a feedback network. Oscillators begin as soon as the DC power is applied without any external input. So this particular DC power or the voltage what you're giving is to turn on the uh, amplifier, that's it. So once this is on, the oscillations will start being produced. This is due to the noise signal produced in the resistors and other components which is going to be amplified. Clear? To start the oscillations, initially we will keep A beta value to be greater than 1, and then to get a sustained output of the loop, the gain will be kept to be equal to 1. Now what is the meaning of this is, you can see here. So we will see the three different conditions for A beta. That is, if I keep my A beta, that is the closed loop gain factor, that is A into beta, the product, if it is greater than 1, you can see the oscillations that is being produced. So initially this particular signal, if you can see, the amplitude is increasing exponentially for this particular condition. Can you see here? That is when A beta is greater than 1, my particular amplitude will increase exponentially. But similarly, if you see A beta lesser than 1, the oscillations will start decreasing exponentially. Clear? So these two kind of oscillations are called damped oscillations. Right? They are called the damped oscillations, where they either exponentially increase or exponentially decrease. Now when I tell sustained oscillations, I need to keep my A beta equal to 1. Now this is one of the Parkinson criteria, right, where A into beta should be equal to 1. So if you keep it at this particular condition, we will get something called as sustained oscillation. That is an oscillation of constant amplitude and constant frequency. Clear? So this is the end of today's class. In the next class, we will see RC phase shift oscillator. Thank you. So the first application, that is the RC phase shift oscillator. Now we can see that the RC phase shift oscillators are used to produce the audio frequency applications. So audio frequency range is somewhere between 20 hertz to 20 kilohertz. Now kilo stands for 10 to the power plus 3. RC phase shift oscillators produce a sine wave output, and we clearly told that in an oscillator we will have an amplifier and a feedback circuit. So here in the RC phase shift oscillator, it consists of an inverting amplifier which produces a 180-degree phase shift. We know that inverting amplifier will produce 180-degree phase shift, and we will use a feedback circuit which will have three RC sections, that is resistor and capacitor sections. Each will produce a phase shift of 60-degree. So if each RC section is producing 60-degree, so 3 into 60, that is 180. And already, so because of the feedback circuit, I have a phase shift of 180. And because of the inverting amplifier, I have a phase shift of 180. So 180 plus 180, I will have a total of 360-degree. Now we know that the Parkinson criteria, the entire phase shift of the circuit should be either 0-degree or 360-degree. So that is being satisfied here. So let us see this particular circuit. So here, once you are applying this DC supplies, that is plus VCC and minus VE, we can see we are not using any other input here. So without any, so what is an oscillator? It produces constant oscillations of constant amplitude and frequency without any application of the external input. So here I have a inverting amplifier. You can see here I have an inverting amplifier starting from this point to this point. We have an inverting amplifier which will produce 180-degree phase shift, and I have three RC sections. Each of them will produce 60-degree. So 60 plus 60 plus 60, 180, and 180-degree phase shift produced by this. So that will be 360-degree. Clear? So in this feedback circuit, the input of the feedback circuit is V out and the output is VF. Clear? So this is our feedback circuit. The input to the feedback circuit is V out and the output of the feedback circuit is VF. Right? Now we can clearly see that each RC section can produce a phase shift of 90-degree maximum, and the number of RC stages helps improve the frequency stability. That is, my frequency of the oscillations will remain stable depending on the number of RC stages. If n stages are used, then each RC section is designed to produce a phase shift of 180-degree divided by n. So for example, in this particular case, we have used 3 RC sections. So 180 divided by 3. So that is why I am having 60-degree phase shift from each RC section. Clear? Now we can use only 2 RC sections, so that, but here if you use 2 RC sections, each RC section is producing 90 degrees. So 90 plus 90, 180-degree phase shift you will get, but your frequency will not be stable. Clear? And therefore we are using 3 sections which will improve your frequency stability. You can also go for 4 RC sections, each producing, that is 180 divided by 4, that is 45 degrees each RC section is going to give. But what happens is your frequency stability will be better, but the complexity of the circuit will increase and even the cost will increase. That is why we are going for 3 RC sections. Now if we go further, now frequency of oscillation of this particular oscillator is given by f naught, which is equal to 1 by 2 pi r into c root 2n. Now n stands for the number of RC sections. So for this particular circuit, we know that n value is 3 because we are using 3 RC sections. So f naught is equivalent to 1 by 2 pi rc root 6. And we know that this is your feedback factor or the attenuation factor, that is beta, which is given by Vf by V naught. We will choose it as 1 by 29. It is a standard value, 1 by 29 for the RC phase shift oscillator. Now to meet the Parkinson criteria, initially we are going to keep A beta. Initially we are going to keep the modulus of A beta should be greater than 1 because I want my signal oscillations to increase, right? So if I keep A into beta which is greater than 1, so if I shift if I substitute the beta value as 1 by 29, I can shift 29 to the right side. So the gain should be greater than 29. So the closed loop voltage gain for the inverting amplifier, we know that for the inverting amplifier, the formula for gain is minus RF by R1. So to start oscillations, initially we have to keep it A beta greater than 1. So if I keep the gain greater than 29, so RF by R1 should be greater than 29. So I have to choose RF to be greater than 29 times R1. And once the oscillation are increasing, after that I will make that A beta equal to 1. So RF will be equal to 29 times R1. Then I will get a sustained oscillation. So this completes the RC phase shift oscillator. In the next class, we will see the Weinbridge oscillator.